Hello, and welcome back to AP Physics. Going a little bit more into free body diagrams. If the forces completely cancel out, if all the forces are balanced, or if the sum of the forces equals 0, then we know that the up forces balance with the down forces. So that's why we've got the blue hash marks. And the left force is balanced with the right forces, if there are any. And that's why we've got the double hash marks to show that those are the same, but not necessarily the same as the up and down forces. So if this object was moving to the left, what would be happening to its velocity? Okay. Well, if the sum of the forces are 0, it would be moving at a constant velocity to the left. If it was moving to the right, then it would be moving at a constant velocity to the right. Same with up and down. Okay, sometimes the forces don't balance. So here, we've got the forces balance in the x direction, in the left and the right they balance, but we've got a downward force. So our net force would be down, and if this object was moving upwards, what would be happening to its speed if it had a downward force? And it would be slowing down. And if it was moving down and it had a net force down, it would be speeding up. Okay, so here we've got another example. The up and down forces cancel in this case. The sum of the forces in the y direction equals 0, but the forces in the x direction don't cancel, and we have a positive force in the x direction to the right. So if this object was traveling to the right and it had this free body diagram, what would be happening to its speed? It would be speeding up. Since the net force is to the right and it's moving to the right, it's going to be speeding up. Okay. What would be happening to its speed now if it was moving to the right? Well, there's still a net force to the right, so it would be speeding up to the right as well. Okay. What about the forces? Are they balanced now? Yeah, the forces are balanced. What would the object be doing if it was moving upwards? Would it be moving upwards, speeding up, slowing down, or moving at a constant speed? Well, since the forces are balanced, it'd be moving at a constant speed. Throwing just a couple simple numbers at this, what would the force of tension be if the weight of each of these weights was equal to 50 newtons? What would the force of tension in this rope be? Well, it'd be 50 newtons. Well, what would the force of tension be if we had 2 ropes? There'd be 25 in each, and I'd have 25 newtons up and 25 newtons up and 50 newtons down, and that would still balance out, and my forces would cancel. Okay, let's draw a free body diagram for a baseball player who is sliding to the right and slowing down into second base. So are the forces balanced on the baseball player? And you got to ask yourself, is the baseball player stationary? No. Is the baseball player moving at a constant speed? No, he's slowing. So that means the forces are not balanced. Okay. What's the direction of the net force? If he's moving to the right and he's slowing, that means that the direction of the net force has got to be opposite. Okay, so the net force has got to be acting to the left. So let's fill in our free body diagram. So what are the forces acting on the baseball player? Well, we're on planet Earth, so that means we got gravity down. Okay, the force of gravity on the baseball player by the Earth. Okay. Now the baseball player is not accelerating downward. Okay, he's accelerating to the left. What does that tell me about my upward force? Okay, my upward force has got to balance and cancel out with my downward force because the forces are balanced. So we should have hash marks here. I don't know why I don't have hash marks. Now, is there any forces acting to the left or to the right? We already know that there has to be. What is a force acting to the left or to the right? Well, friction would be our major force that's acting. And which way is the friction going to be acting? If he's sliding to the right, it's going to be acting to the left. So to the left, we've got a force of friction on the player by the dirt or ground or whatever. Okay. Oh, there's our hash marks. Any forces acting to the right? Okay, he's moving to the right. Are there any forces acting to the right? No, there are no forces acting to the right. Okay, why is he still moving to the right if friction is slowing him? Because of inertia. Okay, it takes time for him to slow down. It doesn't happen immediately. So anyway, that is that. Let's make some free body diagrams for. I have a little disc, and when you turn it on, it has fans, and the fans blow, and it makes it ride on a cushion of air, and it's pretty cool. Once you give it a push, it'll glide frictionlessly over a smooth floor. So we're going to draw some force diagrams for that. So here's my hover puck. Okay, here's the floor, the table, whatever it's on. And okay, so my hover puck is off and stationary. So what are the forces balanced or unbalanced on the hover puck? Well, if it's stationary and remaining stationary, then the forces are balanced. So all my forces have got to cancel. My ups and downs have got to cancel. My lefts and rights have to cancel if there's any forces in all four directions. So let's see, what's the force acting on the hover puck? Well, we got gravity. We got gravity going down. So there's a force of gravity on the hover puck by the Earth. Okay, since the forces are balanced, since the sum of the forces equals 0, there's got to be an upward force canceling that out, or upward forces. Okay, but in this case, there's just one, and that is the what? That is the normal force. So there's a normal force on the puck by the table. Okay, any forces acting to the left or to the right? I do not think so. Okay, but we do put our hash marks to show that they're balanced. Now let's turn the hover puck on. And now we see that it's no longer sitting on the table. It's actually on a thin cushion of air, but it's still stationary. It's still stationary. So that tells me that the forces are still balanced on it. Okay. What's going to be different about this free body diagram? It's levitating a little bit and it's still stationary. Is gravity going to change? No. There's a force of gravity on the puck by the Earth. There's still an upward force because the forces have got to balance. What's going to be different about the normal force? Well, it's no longer touching the table, so it's the normal force on the puck by the air. Okay. Next, we're going to get it moving by giving it a push. So it's speeding up to the right due to a push. And we'll say my hand is pushing it, or my foot, or something like that. So forces on the free body diagram. Are the forces balanced or not? Okay. Is it stationary? No. Is it moving at a constant speed? No. Okay, that means since it's speeding up. Okay, yes. That means it's got to be the forces have got to be unbalanced. And since it's speeding up to the right, that means that the net force has got to be to the right. So let's look at the forces acting on it. So we got down, the normal force, or I'm sorry, force of gravity on the puck by the Earth. Okay, we still have our normal force up. There's a normal force on the puck by the air. And then those are balanced. The unbalanced force is to the right, and that is the push. So there's a normal force on the puck by my foot. So I gave it a kick. So it's not on the table. It's on the floor. Okay. All right. Now let's say that I stop kicking it, and it's gliding along at a constant speed. So it's on a frictionless surface, and it's gliding along to the right. Picture it gliding. Are you picturing? Gliding. So let's look at the forces acting on this. So first off, are the forces balanced or unbalanced if it's coasting to the right at a constant speed? The forces on it are balanced. So all my ups have a down and my lefts have a right. Okay. So let's look. Do I still have gravity? Still have gravity. Force of gravity on the puck by the Earth. Do I still have the normal force? Still got the normal force. Okay. Now, right now, my forces are balanced. Are there any forces acting to the left or to the right? Think about that. My foot's no longer touching it, so I don't have that force. Okay, it's moving to the right. Are there any forces that are causing it to move to the right? No. Okay. The forces on it are balanced, which means that it's just going to keep doing what it's doing. So since it's coasting to the right at a constant speed, the forces on it are balanced. To get it moving, I had to exert an unbalanced force. To change its motion, I have to exert an unbalanced force. But in order to keep it moving, okay, the forces are balanced. Okay, let's draw a free body diagram. We've got a girl here who's stretching her calves, doing the wall stretch. So let's draw a force diagram for her. Okay, so let's see. Forces acting on the girl. We've got gravity, force of gravity on the girl by the Earth. That's down. Okay. Oh, I guess I forgot to mention. I forgot to question you. Are the forces balanced or unbalanced on the girl? Okay, she's at an angle diagonal to the wall, stretching on the floor. Okay. Well, what's happening to her motion? Is it constant or changing? It's constant. That tells me that the forces are balanced. So all my ups need a down and my lefts need a right, if there are them. Okay, so that means I need a force or forces going up. Okay, what's the force that's keeping her from falling down? There's a normal force on the girl by the floor. Okay, any other forces acting on the girl? Yes. Okay. There's a force. Oh, I forgot these are balanced. Okay, there's a force on the girl by the wall, okay, where her hands are touching the wall. The wall is pushing her to the right. Okay. Now, if the forces are balanced, I need one more force, or at least, because I got to cancel this force out. What is the force that we're missing? I'll give you a hint. It's happening down here by her feet, or on her feet. Okay? I'll give you another hint. What would happen if I were to spray some oil on this floor? Is she going to stay like this? No. Okay? It's because there's friction, and friction is keeping her, is pushing her to the left. And that's what balances everything out. Okay, think back to previous unit when we could take a diagonal and we could break it apart into its components. Remember doing that? Okay. We're going to do that in this unit, although we're not going to get out rulers and protractors or anything like that. We're just going to kind of sketch things. But so if I have a diagonal force, I can have a force in the x direction. It can have a component in the x direction, and it will have a component in the y direction. So, and I usually use the dashed lines to designate those forces. So if I have an object and it's got three forces on it, and it's not accelerating, so this is my force diagram, although I didn't label with the gravity and normal and all that. If the forces on it are if it's not accelerating, and then the forces all have to cancel, which means that this thing has a horizontal component and a vertical component. The horizontal component of Cx, okay, has to cancel out with the force A to the right, okay, and the vertical component Cy has to cancel out with B. Okay, so just showing you that you can break these apart into its components and show that the components will cancel out with other forces. Okay, let's do a one where we've got a weight and it's being pushed on by a rod, and then there's a cable also supporting it. Okay, and what we're concerned about with is this weight in this ring, but what does consider this one object, the weight. Okay, so everything is stationary, so what does that tell me? It tells me that the forces are balanced, so my ups and downs cancel, my lefts and rights cancel. So let's see, forces acting on my weight. Well, we're on planet Earth, so we got gravity going down again. So there's a force of gravity on the weight by the Earth. Okay. What other forces are acting on the weight? We've got a tension force, this cable, which is going to be a pull at a diagonal. Yeah, I didn't make my angle quite perfect, but you get the basic idea. So I got a diagonal pull from the cable, so force of tension on the weight by the cable. Okay, do the forces look balanced? No, they do not look balanced. These two forces cannot cancel, okay, which means I need another force. And that force is supplied by the rod. Which way is the rod exerting a force on the weight? To the right, okay, because if I got rid of this rod, this thing would swing inward to the left, so it's being pushed to the right. So there's a normal force on the weight by the rod. Okay, showing you just what I showed you. Looking at this, we can break this apart into a component vectors. Okay, and now I can say that my vertical component of tension cancels out with gravity. Okay, and my horizontal component of tension cancels out with the normal force. So just an example of seeing that. Let's see. The last thing I want to show you today is a trick that we do when an object is on a sloped surface. So here we've got a box that's on a sloped surface, and it's stationary. That tells me that the forces on it are balanced. We've got the force of gravity down. We've got the normal force. Notice that the normal force is perpendicular to the slope. And if it's stationary, okay, there's got to be another force. Another force has got to help cancel this out. What's my missing force? What's preventing it from sliding down the slope? Friction. That is right. So we've got a force of friction acting down, acting up and to the left. So here's what we're going to do. We know that these three forces cancel. But right now, I can't. I've got two diagonals, and I don't really want to mess with breaking apart two diagonals into the components. So what we're going to do is play a trick. We're going to rotate the page. Okay. See, I don't know if you see what I did here. I took this slope, and I'm going to rotate it flat. Okay. So now the ramp is flat, and gravity is at a diagonal. Okay, so you literally just tilt the page, like on your desk, tilt the page. And now if I want to show that everything cancels out, I've only got one diagonal. Okay, I show that the ups and the downs cancel, so that this vertical component, quote unquote vertical component of gravity, cancels out with the normal force, and this horizontal force of gravity cancels out with the force of friction. One thing I want you to make note of when you do this, notice that the right angle is opposite the force of gravity. So that's the hypotenuse is the force of gravity, and the diagonal is across, or the 90 degrees is across from the force of gravity, and that the normal force and this component of gravity are parallel. And so are this component and the force of friction. Okay, so this is a component that's perpendicular to the hill. And this is a component that's parallel to the hill. And that is where we're going to end up skipping that. With that, so what we're going to do is work on 4-3. There's several of these, so I'm going to give you some time to work on this. I don't know the exact due date offhand, but look on here. I think I give you at least 2 days to work on this. So do that, and good luck.